Just coming up to 12:01, so shall we commence? Good morning, CIBSE colleagues and other people who have occurred to join this event. Thanks for taking time to register this masterclass CPC series. This is our third event for CIBSE Merseyside. And it's been really successful, and I hope you enjoy it this morning. My name is Henry Gunway. I'm the Deputy Chair of CIBSE Merseyside and North Wales region and Social Secretary, and I'll be your host this morning. Before I commence, there's a few ground rules which are covered off on the slide. So primarily, all the attendees will be muted and the video will be off, and only the speakers will be on view. And I'll actually fade from view after I've stopped speaking. All attendees will be requested to put their team's names that should appear on your CPD certificate, which will be issued by CIBSE. So Samsung Galaxy 10 or my mum's iPhone just doesn't cut the mustard with CIBSE for CPD, and it looks pretty awful as well. So if you can actually just change your device names, that'd be good. If you've got any questions, just put them into the chat as well, and hopefully don't actually post any bogus names like Queen Victoria or Mickey Mouse, because this is not the weekly quiz. All questions, if you post to the chat, and they'll be moderated after the event, and any unanswered questions hopefully will be answered by Graham or myself by email, or by you contacting Graham either on LinkedIn or on his email address. So do contribute your questions, and I'll facilitate the Q&A at the end. So our speaker this morning is Graham Barker, who's the Director of Vertical Transportation at Cundall. Cundall is obviously a Premier League consultant practice in the UK and also globally. Well-known fact about Graham: he's a chartered engineer and a fellow of the Institute of Mechanical Engineers, and certainly an active CIBSE member, and he's chaired many symposiums on this subject. Little known fact: he graduated in mechanical engineering from Newcastle University, and he's worked most of his career in the lift industry. He's definitely a serial blogger, a keen person on Twitter, and has probably the largest internet footprint I know of any person on this planet. I'm delighted to hand over proceedings to Graham, who's kindly offered to take questions during and after the presentation as required. Cheers, Graham.
Thanks, Henry. I'm not sure I can live up to the accolade of the social media footprint, and I'm sure there's others in the social media space that are probably more prominent than I. So welcome everybody. As Henry said, I lead the vertical transportation team at Cundall. My contact details are on the screen, and they'll also be repeated at the back end. So really, today's agenda, we're going to talk about different types of lift technology. We're going to talk about accessibility, evacuation and firefighters' use of lifts, communication systems for lifts, working with design teams in and around the kind of topic of lifts, and just some kind of common issues, tips and tricks that come up quite frequently when we're looking at vertical transportation design. So a little bit about Cundall. So as Henry said, we were established in 1976 in the UK in Newcastle, but we're now 24 offices globally, just over 1,000 people. We're on a journey for all of our projects to be net zero carbon by 2030. So generally we started in the UK, and then we kind of went over towards the Asia Pacific direction and have offices throughout the UK, Europe, Middle East, and in Asia Pac. Vertical transportation is just one of the many services that we offer. Essentially, I suppose you could term us as a full service engineering consultancy, with everything from acoustics at A to vertical transportation at the back end of the alphabet and everything in between. We operate in all sectors, be it aviation, critical systems, through to kind of residential and workplace. We like to enter awards and I've been lucky to win a few. Only last week, I think we won building consultant performance consultancy of the year. And as I said, we're working towards a 2030 net zero challenge. And specifically in terms of vertical transportation, the areas that my team are supporting that is in around reducing operational energy demand and consumption, and also looking at whole life carbon in conjunction with whole life costings. As this is, I suppose, an opportunity to speak to some people that may be early in their careers, I just wanted to signpost you to a little bit of information about our early career schemes. So we operate graduate schemes, placements, apprentices, and work experience schemes. And if any of those are of interest, please do contact us through all the various channels. Our graduate applications go live in September of this year for 24. We've currently got placement and apprenticeship processes ongoing at this moment in time. So if you think Cundall might be the place for you, please do reach out. So I suppose question really, what is vertical transportation? And essentially it's quite a broad field, from lifts that maybe help those in a wheelchair up 2 or 3 steps into a building, to the 10-meter a second lifts that take you up 300 plus meters in the Burj Khalifa, to great big industrial things that can lift massive weights, whether that be an HGV truck, a crane, or something similar. But the main crux of it really is passenger lifts, goods lifts, escalators, and moving walkways or travelators. So really, when we're involved in the vertical transportation field, we're often involved in the whole life of a building, from the initial kind of conceptual planning stages through building design, working with other members of the design team, be that the other engineers, be that the architects, operators, through construction, and also in operation and maintenance of buildings and renewal and refurbishment. The typical lifespan of a building is around about 75 years. Typical lifespan of vertical transportation equipment is normally around 20 to 25. So during the lifespan of a building, you tend to get, probably at least 2 refurbishments of the vertical transportation assets just during the life of the building. So looking at a little bit of terminology, because sometimes terminology can be confusing or misunderstood. So essentially, looking at a lift shaft in vertical section, there's 3 main areas that we talk about. The pit, which is the space below the bottom floor, typically something in the region of 1 meter to a couple of meters deep, and that's really related to the speed of the lift. Then you have the travel, which is effectively from the lowest floor served to the highest floor served, the amount of distance that the lift actually travels vertically. And then above that top floor, there's a headroom space, which, dependent on design, will be something in the region of 3.5 to maybe 5.5 meters, and depending on the lift design, may have an amount of equipment within it or not, as we'll see in a couple of slides time. Looking at things in plan, so over on the left, the lift shaft depth runs from the front wall to the rear wall. The lift shaft width runs from the left-hand side to the right-hand side wall, and it's amazing how many times in projects those dimensions get switched. So what's really important when looking at lift shaft design is that actually the depth and the width are in the right planes and in the right relationship to the doors. And you'll see there are a number of other kind of key dimensions, but the one that I would always recommend people to keep an eye out for is that depth and width, and that it's in the right orientation to the doors when planning a building. So the variety of different, I suppose, components, elements of a lift system. Drive systems, typically electrical or hydraulic. Safety systems, door systems, control systems, and then the hoistway equipment and the car in traction, electric traction lifts. You also have a counterbalance or a counterweight, and really that's to reduce the energy used by the lift. So rather than, let's say, the weight of a lift car is 1,000 kilos and it's got 1,000 kilos in it, rather than lifting 2,000 kilos every time, there is a counterbalance to make it a more energy efficient journey. So typical kind of types of lift system. So in the electric traction, you get machine room above. That's the kind of traditional arrangement. Was very prevalent up until the mid to late 90s. And now you will typically only see machine rooms on tall buildings or perhaps specific buildings where access to plant is important, like hospitals. The majority of lifts today will be machine roomless, meaning that they don't have a room on the roof for the machinery. All the machinery is within the lift shaft. And then hydraulics, effectively, I suppose the difference with a hydraulic is often the lift is being pushed up from underneath by hydraulic pressure, and so the machine rooms for a hydraulic lift are often at the lowest floor of a building. They can be in other places, they can be remote, but typically they would be at the lowest floor and next to the lift shaft. And thinking about kind of application of those different technologies, if I can start over on the right hand side with the hydraulics. Hydraulics are perfect for slow speed but high weight, yeah, or high load. So when you've got particularly large goods lifts, lifts for carrying cars, for carrying HGV trucks, things of that nature, over short distances typically, then hydraulics are absolutely perfect for that kind of thing. Large rated loads, simple construction, low speed. Traction lifts are, which are the electromechanical ones, much more kind of universally applicable, and with speeds from 0.1 meter a second up to around about 10 meters a second. Very large range of travel. Tallest lifts are up to around 500 meters tall in buildings now. And with rated loads from kind of a few hundred kg to maybe 10,000 kg. So in terms of applicability, the electric traction lift has got the widest range of application. And as I said earlier, since around about 2000, then machine room lifts have become much more prevalent as the common solution for electric traction lifts. And in the early days, that was quite restricted, maybe low speed, small lift cars. But now we've got machine roomless lifts of pretty much every size and shape, up to 3.5 meters a second, and over 100 meters of travel. So this is an arrangement with the machine room above. So as you see, you've got the lift shaft with the lift car going up and down between the floors, and then above all of that, you have a room where the machine, the controller, the electrical connections are all contained. The difference with a machine roomless lift is really that equipment has just been moved into the top of the lift shaft typically. In order to do so, it's been made smaller. As technology's improved, electronics have become smaller, machines have become smaller. It's provided the ability to house that equipment within the top of the lift shaft and save that space. And then, as I mentioned on the hydraulics, typically you have a room adjacent to the lowest floor of the lift shaft and a hydraulic cylinder that is possibly pushing the lift car up with directly from underneath, possibly involving some kind of pulleys and roping to assist with the loads involved. but essentially is a pushing up movement, and then hydraulics tend to travel downwards more by gravity than anything else. So some of the things that we need to think about when designing a lift system for a building really is identifying and developing the design criteria. Often that'll be around how many people do we need to move at peak times. So for argument's sake, the volume of people using a lift in a busy office building is going to be an awful lot more than the volume of people using a lift in a car park. And some of the things that or the key metrics that are also taken into account there are things, the waiting time and the time to destination. So the waiting time being the time that somebody would, you press the lift button, how long do you wait before the lift arrives? And then the time to destination is from getting into the lift car to effectively getting out. And the level of performance that's acceptable to people is very much dependent on the environment. In an office building, it's quite typical that waiting times would be less than 25 or 30 seconds as a maximum, whereas perhaps in a residential building, up to 55 seconds would be an acceptable waiting time, because there is a balance really between having enough lifts to move the people within the building, but not having that many lifts that actually you're building a building to house lifts. You want some floor plate left. You want to, the purpose of a building is not really to house lifts, it's to house the people that are doing whatever they're doing on the different floors, whether that be offices, flats. And so minimizing the footprint that's taken up by the lift shaft is key to the design development. Other things to take into consideration are also the physical size of objects that are moved regularly. So maybe in residential, that might be furniture, might be deliveries, but also those things that are moved rarely. So quite often lifts will be part of the plant replacement strategy for a building. And so if a generator is located on a particular floor and there's a potential that that needs to be removed or replaced using the lift every 10 years, then that lift needs to be suitably sized to be able to take that irregular event. And also the other elements that come into, I suppose, the design criteria for vertical transportation are around, will the lift be used as part of the firefighting strategy? So typically buildings over 18 meters tall in the UK would have firefighting lifts. Will the lift be used to help with the evacuation of people? So that, evacuation using lifts could apply to any building with a lift from 2 stories and above. And also, how will the lift interface with the security arrangements of the building? Is the lift itself some kind of preventative measure to stop people getting to and from certain floors? The other major factor when thinking about lifts is about accessibility. So the building regulations part M define the requirements, the minimum requirements for accessibility of buildings, and they provide this very nice diagram that basically details a lift that is 1400 deep by 1100 wide. So it's a 630 kg 8-person lift. And one of the problems that we see frequently is that this minimum requirement then all kind of becomes the de facto standard. But what also is relevant in association with accessibility are there are specific a specific standard EN 8170 which relates to the accessibility to lifts for persons with disability, and doesn't just think about individuals in a standard wheelchair. It looks at physical disabilities, sensory disabilities, cognitive, so there are many different issues that have to be handled by lifts and in terms of accessibility, and Part M really needs to be seen as just the minimum standard. If we look at the table here is taken from that EN 8170 accessible lift standard, and the line in red, line 2, is basically the size of lift which is determined in building regulations Part M. And what you'll see is there are actually another 3/4 larger sizes that are more relevant for certain situations. Essentially, the Part M basic lift can accept an accompanied manual wheelchair. It's unlikely to be able to accept people in an electric wheelchair. It's definitely not going to be able to accept people on stretchers, things of that nature. So when thinking about the design of lifts, building regulations Part M is a minimum requirement, but we really need to think about how is this lift going to be used and how is it going to be accessible for all. For those of you that are not aware of the various wheelchair classifications and sizes, the Class A manual wheelchair on the left-hand side is relatively straightforward and will fit within that basic lift size that we saw earlier, whereas the larger electric self-propelled wheelchairs generally need much larger space, particularly for turning as well. So it's really about making sure that we're accessible for everybody. In more perhaps residential developments or developments where you get perhaps a more aged mix of residents, then motorized scooters is a key factor these days. Many residents will have motorized scooters and will want to be able to get those motorized scooters to their flats, or may even need to be able to get to their flats on motorized scooters. So thinking a little bit now about lifts for evacuation and firefighters lift use and some of the specific requirements around those. So firefighting lifts have got a standard all by themselves, which I'm not going to go through the detail of, but the key kind of fundamental requirements of that are that they have a secondary power supply. So typically that's going to be a diesel generator. It's unlikely at the moment that a UPS solution is going to be able to supply a firefighting lift, though I think we're moving towards that situation. The alternative is that the secondary power may come from an alternative power supply source to the main supply of the building. Firefighters lifts have basically 2 stages of operation. In the first stage, they return to the escape floor to park and be available for the fire service. And then when the fire service arrive, there's a specific control mechanism that they have. There's a minimum size. Coincidentally, that minimum size is also the minimum size that we saw in relation to the accessibility of lifts and Part M. But there's more and more call from the fire service that actually this minimum size is just too small, particularly for the kit that they have to transfer if they need to evacuate any injured parties on stretchers. So this minimum size of firefighting lifts very much needs to be seen as a minimum, and I think in the not too distant future we may well see that changing. Firefighting lifts have have automatic doors, minimum door width of 800 millimeters, and a minimum fire rating of 60 minutes. But actually, their fire rating is linked to the fire rating of the structure in which they are contained. So if the structure around the lift shaft is a 2-hour fire rated, then the lift would be 2-hour fire rated. Something that's often queried and is important to be aware of: lift doors don't have smoke seals. So if you need to smoke seal a lift door, typically you will have a fire curtain or fire shutter in front of the lift doors in order to provide that smoke seal as well as the fire rating. Firefighting lifts have to be able to access the furthest levels of a building within 60 seconds. They also have some facilities to allow firefighters to be rescued in the event that the lift was to break down with the firefighters in it. And they have water protection measures so that when the sprinklers are going off or water is sloshing around in the building, it doesn't disable the lift. So that was the standard for firefighters lifts has been in place since around about 2015. But for anybody that's involved in kind of refurbishment of buildings, what we've got is a situation that's developed over many, many years since the first standards being issued in around about the 60s. So we have a fire recall feature, which basically calls the lift down to the lowest floor, and often that would be either a manual switch, or today it would be connected to the fire alarm and be automatic. So in aged buildings, you may have a switch adjacent to the lift that effectively is performing the function of a fire alarm connection. You've also got lifts for firefighters' use, and we've had firemen's lifts between the 70s and 80s. We've had firefighting lifts between the 80s and early 2000s, and now we've got firefighters lifts. And the requirements or the provisions of each of those different types of lifts is very different. And so, a fireman's lift from the 1980s is a very different lift to a firefighter's lift of the present day. So if you're working in existing buildings, and particularly when you're looking to upgrade or redevelop existing buildings, it's really important to understand what are the provisions that are there already, and practically and feasibly what can be upgraded, what changes can be made. And then evacuation lifts. Well, evacuation lifts have existed as a thing since the 1980s and are defined in BS 9999. There is currently a revision of BS 9991, which is the fire safety for residential buildings. That's currently going through at the moment and is due for publication later this year, and that will likely change the requirements for evacuation lifts. In parallel to that, but not directly connected to it, there is also a European standard under development specifically for evacuation lifts, which would likely be implemented in the UK, even though we're no longer part of Europe. So one of the key things for existing buildings is actually understanding what type of firefighters lift there is, and in reality, firefighters are not experts on lifts or on firefighters lifts, and they don't know whether they've got a fireman's, a firefighter's, or a firefighting lift. So some really simple signage within building design is key, just so that when the firefighters arrive, that they've got awareness of what is this lift in front of me, can I use it, is it safe, what features does it have. And under the Building Safety Act, this is also something that forms part of the safety case for high risk buildings, so you're likely to see this more and more over the course of this year, really, as we see those safety cases being implemented. So in terms of evacuation lifts, I mentioned the standard that they comply with earlier. They're quite similar to firefighting lifts, but not quite as complex. They have a secondary power supply, which may be a generator. You're more likely to see the potential of a UPS solution for an evacuation lift, and that's primarily because an evacuation lift will be designed to perform a set number of evacuations. So the UPS can then be sized to provide the appropriate level of power and for duration to meet those number of evacuations. You also have in the secondary power solutions the potential of just a diverse routed supply from the same power intake, so that if the primary supply failed, you've got a diverse routed supply through a fire protected enclosure, providing that secondary power supply. So it's a little bit simpler. There's an evacuation switch at the main exit 4 that puts it into an evacuation mode in a similar way to firefighting lifts, which have a firefighter's switch, putting it into a firefighter's mode. And there's a communication system, which is also similar but slightly different from a firefighter's lift. I think the key thing with evacuation lifts under the current regulations is the use of that lift to evacuate people is a managed evacuation. So typically, what does that mean? If you've got a person due to be evacuated from an upper floor, there will be an evacuation management team of at least 2 people, one of whom will stay at the main floor to effectively control the evacuation. A second person will then get in the lift at the main floor and take that lift to wherever the evacuee is, get the evacuee and bring them back in the lift. So evacuation lifts of themselves do not evacuate people. They need to be supported by trained evacuation teams that can use them. One of the developments that we're likely to see in the change in standards is going to be the potential of self-evacuation or some kind of automated evacuation, and that's in the draft revised standards, but we're waiting to see how that plays out when those standards are published later on this year. I know we're presenting to the Northwest chapter today, but for those of you that have involvement in working or deal with projects in London, the London plan may have some relevance for your projects. And key thing in there is that the London plan has a specific requirement in it that there will be an evacuation lift in each core of a multi-storey building. So London has kind of raised the bar on their requirements for evacuation lifts. Similarly, I know that the Liverpool kind of planning and building control authorities have a strong desire for evacuation lifts in many of their buildings as well. You may or may not be aware that the Fire Safety England regulations, which were ratified in 2022, came into effect about 5 or 6 weeks ago, and they relate to existing buildings in England and bringing in a regime of testing and inspecting for lifts that are provided for use by the fire service or for evacuation. So there's now a requirement for building owners and operators who have lifts, firefighters lifts or evacuation lifts in their buildings to notify the local fire service if that lift is broken down or is for some reason unavailable for more than 24 hours. And also that it's regularly maintained, inspected, and that records are kept. Moving on now into kind of lift emergency communications. So since the late 90s, new lifts have needed to have the ability for a trapped passenger to contact a rescue service. Generally, this is termed an auto dialer because it does all the dialing by itself. Long have gone the days where there was a physical telephone within a lift. So it's a hands-free communication device that should automatically connect to a rescue service. Typically, that rescue service is going to be the lift maintenance provider, and that system would identify where, as a trapped passenger, where you are, what lift you're in, and effectively notify the rescue service so that they can come and rescue you. It's got audible and visual indication for lift users, so keeping that kind of accessibility for all. So even if you were deaf, for example, you could activate the auto dialer, and because they should know your location already, and you've got visual indication of its operation, then it's still appropriate for that use. That auto dialer system needs to have an emergency power supply. So because quite often people get trapped in lifts, not because the lift fails, but because the power supply to the building has failed. And typically the auto dialer would connect to the outside world using a BT phone line or a GSM phone line. And there's a requirement in the standards for that to undertake a self-checking sequence at least every 72 hours. What's happening at the moment, which slightly changes that and is important for those involved, particularly in the design of new buildings or the modification of buildings, is something called the Great Switch Off. So basically, BT are phasing out analog phone lines by 2025. So that means that over the next couple of years, the availability of an analog phone line for a lift auto dialer or anything else is not going to be available. That gives us two real issues. So I mentioned about the need for the auto dialer to have a backup power supply. So many of the previous iterations of auto dialers actually took their power from the phone line. The BT phone line has got a voltage, and so it had sufficient voltage to power the auto dialer itself. So turning that phone line off actually kills the power supply to the communication unit itself. But also, and so effectively, we're now moving to analog GSM communications for almost all communication systems. We do get requested about VoIP systems, but typically VoIP systems go through a computer system within the building. And the issue there is if that VoIP system needs to be battery backed up at every stage throughout its design. So the computer that's running the phone system needs to be battery backup, needs to be self-checking, etc. So moving forwards, I think analog phone lines are going to be phased out, and probably on any projects to now should not be considered. And we're moving towards GSM. 2G is also being phased out on GSM, and so 4G is the best GSM technology that's available today for lift communications. Some lifts, may also need to be designed to be able to defend against levels of vandalism, and there are three different types of vandal resistance according to the standards, effectively defined as category 0, 1 and 2. Category 0 is that it has no vandal resistant measures essentially. Category 1 has got some moderate measures to protect against vandalism, and category 2 is much more stringent and well built, shall we say. So for example, category 2 is likely to be seen in public areas that are open to vandalism. Category 1 may be seen in perhaps schools or universities where it's not necessarily vandalism, but maybe it's misuse or over-exertion use, but not direct vandalism and attack. So just thinking about how vertical transportation kind of works as part of the wider design team for buildings. So we interface between lots of different disciplines. The lifts within a building obviously move typically between all floors. We're involved with the architectural team and the architect, whether that be around finishes, whether inside the lift car, also the doors and around the lift doors, but also in terms of user interfaces, visual alignments. From an electrical engineer's perspective, we're often interfacing with them around power requirements. Previously analog phone lines, now typically GSM phone lines, fire alarm and BMS interfaces, and things like CCTV, Wi-Fi coverage, etc. The mechanical engineers, that's really around heating and ventilation, whether that be for the machine rooms themselves, if there's a machine room, or also for the lift shaft. There's a requirement that the lift equipment is maintained between extremes of +5 and +40 degrees. So that may in some cases need ventilation to be provided, or indeed heating. Often interface with structural engineers around the lift pits and the lift shaft itself, with the acousticians around noise transfer from the shaft to surrounding areas, particularly prevalent in residential developments or hotel developments, where perhaps you've got bedrooms close to the lift shaft and you want to make sure that the noise of the lift operating is not transferred through the lift shaft into those sleeping areas. Interface with the security consultants around access control integrations, speed gates, special modes and features. For example, some buildings may have invasion controls, bomb threat controls. And then with the fire engineers around kind of firefighting lifts and evacuation lifts. So just on the topic of lift shaft ventilation, because it's something that quite often gets misunderstood. So the lift shaft ventilation's the responsibility of the building designer. That's a bit of a vague thing, really. So what that really means is it's a team effort, typically between the lift consultant and the mechanical engineer. The concept design stage, the requirements of the selected lift contractor are not known. So you basically need to assume that there's going to be a need for some form of ventilation. Then once the lift contract is selected, they will provide the heat output of their specific equipment, and that will then enable the mechanical engineers to determine whether ventilation is required or not. Thinking back to what we were saying right at the beginning about our move to net zero, and also keeping heat within buildings, as it were, the days of fixed ventilation louvers that just let the heat escape out of the building whilst keeping the lift shaft cool are probably disappearing. We now want to be looking at some kind of intelligent ventilation for lift shafts that only opens and lets heat escape when the temperature raises above a certain threshold, so that we're not losing heat from the building unnecessarily. So just as we kind of move towards the back end of the presentation, then really just a couple of thoughts on common issues in VT design that we experience on a regular basis. So quite often employers' requirements really just document a minimum, and that is then taken as the requirement. There really needs to be a level of thought that goes into actually, is the minimum suitable for this project, for this building usage? We mentioned already about the accessibility requirements. Also, do those requirements fit with the operational requirements of the building? Minimum size of a lift doesn't necessarily provide accessibility for all, but also the minimum size of a lift, being an 8-person, doesn't provide a great deal of space for moving things. So particularly in residential buildings, if you need to be able to move furniture in, fridges, bicycles, you need a lift that is suitably sized to be able to accept that equipment. And if the lift is too small, the reality is that people are going to find a way to fit a fridge freezer into a lift. They just might damage the lift on the way in or the way out. So also making sure that it's appropriate for its use will result in the life of that lift being as expected and it not being damaged through to misuse because essentially it's been incorrectly sized. As Henry mentioned right at the beginning, I write a few blogs now and again, and just a selection there on the screen. If you visit the Cundall website, you'll see our blog section, and please do take a look at those both on lift topics and many others. And so as we kind of come to the close, I'd just like to thank everybody for their involvement and really open the floor up to any questions that anybody may have following today's presentation.
Thanks very much, Graham. Thanks for that very comprehensive presentation. So there's a series of questions. The first question is from Praktar Hatwell. I hope I'm pronouncing that name right. How are the electrical systems cabling done for lift cars?
So there's what's called a traveling cable or trailing cable. So effectively the lift has a cable that is fixed at a high point within the shaft and then fixed to the lift car and is draped in a loop. So it's a special type of cable that travels up and down with the lift. There's a slight change to that coming because with the I'm not sure, with something called TESREL, which is basically, I suppose, Wi-Fi enabled safety circuits, shall we say, then the future is perhaps cableless, but we're still a little bit away from that point arriving.
Wow. Okay. The second question is, are there any set guidelines of these parameters like waiting times and times to destination, etc.?
Yes, that would probably take about another 3 days to explain, but typically I think the two key documents to think of in terms of guidelines is first and foremost the CIBSE Guide D. So that's a CIBSE publication which talks about the transportation in buildings and the different guidelines appropriate for different types of buildings. So within there, you've got the guidelines for hospitals, offices, residential buildings, etc. The other one that also comes into regular occurrence in office buildings is the British Council for Offices Guide for Specifications, which also specifically provides guidance on the performance of lifts in office developments.
Oh, that's great. This is a very similar question. And could you explain using interval versus waiting time criteria when designing lifts? And also, do you assume the time to the destination to be the same time or similar to the journey time?
Oh, that's a very technical question.
It is,
So,
isn't it?
interval is a calculated measure. So sat with a piece of paper and a pen, you could work out the interval for a lift. It's a calculation. Waiting time is a simulation based approach. So basically, historically, when the calculations were devised for how do you work out the lift calculations, it was a mathematical calculation. And it's quite a long one, but you can work it out as a single calculation. With the advent of computers, we moved into the simulation age where you've got more kind of real life analysis by simulating the different journeys of people arriving to a lift. So they're two slightly different things. Interval is, shall we say, the old money, and waiting time is the terminology that you'd see today. And similarly, journey time is the terminology used at the time that interval was used, and time to destination is the terminology used in association with simulation.
That's great. Thank you. I think you've covered this actually, but it says this is from Mr. Haprel again. Apart from the cable rating, what are the other things that are different from firefighting, evacuation, and normal lifts? So I think you actually covered that on your slide, didn't you?
Yeah, but I'll quickly run through. There's lots of things, but in key, firefighting lifts are designed to have a level of fire protection, so they've got fire rated doors. They have water management, so that's typically that the doors will be raised above the finished floor level, so that water on the floor plate basically drains away from the lift and not into the lift shaft. They may also have some drainage in the lift shaft, so that if water does access the lift shaft, that it drains out. Essentially, that what we're aiming for is that the lift shaft doesn't fill with water to an extent that the lift becomes unusable. What the fire service want is a lift that will continue to operate whilst they are continuing to fight the fire. Particularly in tall buildings, and even 8-10 stories, a firefighter carrying all of the equipment that they need to carry to fight a fire is an exhausting role. And lifts can be really helpful and supportive in that. So water management, fire protection, and then there are also specific controls for the firefighters, essentially.
Thank you. How do you decide whether the building requires an evacuation lift and not a firefighting lift?
It's a very good question. And so really this is where fire engineering comes in. And so it's the vertical transportation engineer, the lift consultant, shouldn't be determining that. That would either come from, most projects these days have a fire engineer on them, and they would determine that requirement. The other place it may come from is building control. So on simpler developments that perhaps don't have a fire engineer on them, they might follow just the British standard requirements.
Thank you. And final two questions. Um, can you give your opinion on using firefighting lifts and evacuation lifts for normal passenger use?
Absolutely, yeah. So the firefighters lifts and evacuation lifts should essentially be normal passenger lifts. What the fire service want is a lift that works when they get there. What they don't want is a lift that's full of other things when they get there. So definitely a firefighting or evacuation lift shouldn't be used for goods, or if it is used for goods, it really needs to be a well managed process, so that the firefighter doesn't call the lift, go to get in it and find there's a fridge inside it, for example. But if firefighters and evacuation lifts are a normal passenger lift, it's much more likely that they are going to be well maintained. They're going to be available for use when the fire service want them.
There's another question here. Is there any specific requirements for the ATS location for firefighting and evacuation lifts? I believe the diverse route for the incomer end near the ATS should the ATS be placed inside another fire rated room?
Yeah, I'd have to refer back to the standards to remind myself exactly what, but from memory, I think the ATS has to be in the same fire enclosure as the lift, which typically is the lobby outside of the lift. So you have the lift shaft, and then you have a fire rated lobby outside of the lift shaft, which is typically where the ATS is located.
Yeah, it's a fire rated lobby. There's another question. Is there any difference, or is there any difference or design concerns for lifts that are installed inside a building?
So I think I know where that question's go. So the question from Quentin, I think, is really around what's the difference between a lift inside a building and a lift external to a building. And there's a number of different factors. The obvious one is the weather. So depending on how external it is, if it's exposed to the weather, then
I
it would
see.
need to be suitably IP rated. What people often forget when they think about water is that actually rain doesn't come vertically, and particularly in Liverpool it tends to come from the sideways direction. So making sure that there's canopies and things to address wind-driven rain is as important as IP rating for just water protection. The other things that often get kind of forgotten about are, the climate in the UK is a varied one. I think depending on where you are today, you might have snow forecast for this week. So, there is the potential that temperatures will fall below the +5 degrees. So there's often a requirement for heating. Now, that's not heating of the entire lift shaft, it's heating of the components that are affected by the temperature. And in some cases, that may involve trace heating if you've got the potential of ice forming. And then on the opposite end of the scale, we do occasionally get sunshine. And so, in some cases, particularly scenic lifts where you've got the potential of solar gain and, heat generation in glazed lift shafts, then there may be a requirement for some kind of cooling for comfort and for temperature control.
It's a great response. That's obviously scenic lifts, isn't it? Good. A couple of statements. There's no more questions. There was a couple of statements. One from Matthias Block. Perfect presentation for new employees not familiar with lifts. Well done, Graham, since you made it. And can the recording be published? I'm sure it can be. It's all recorded. And Ella Sumner from CIBSE will actually send a note out with the CP certificates. And there's another one. Thank you, Graham. It was a great informative presentation. And will the presentation be circulated? And the answer to that question is yes. So as we come to the close, it's 12:57. Can I say thank you very much for all your attendance? I hope you found the event worthwhile. Do have a look at the global website by Cundall. The early career scheme looks really good. Connect with Graham on LinkedIn, and please email myself, Ella, with any feedback. Enjoy the rest of the day and continue to register for the masterclass this week. Thanks very much to Graham, to Ella Sumner, and also all the delegates who attended. Final thing for me, tomorrow's masterclass is on lighting design by Tom Niven, director of BDP, and it will be hosted by Dan Whitley, the honorary secretary and founder of Whitley and Partners. So do join Dan tomorrow. Tom Niven is a great speaker, and you'll really enjoy that as well. Enjoy the rest of your day. Thanks very much.
Thanks all for attending.
Cheers, Graham. Can you stay on the line?
Yeah.
That's great, Graham. Thanks very much. As people are leaving, would it be possible for me to have a chat with you regarding a project on, it's a net zero project at Lancaster University?
Yeah, of course. Yeah. No problem.
So I probably need to be signposted to your team. And it's a project where we're actually gonna, it's a unique project. We're actually going to sort of convert the whole campus from CHP to air source heat pumps. So it's a massive project, but there's a project brief which will be finalized by the end of March, and it'll go out on the Helga framework. And I will send you a note about all this, but I just wanted you to be aware that I will send it up to you, and you can signpost it to your relevant teams. That would be great.
Absolutely. Yeah. Thanks for that, Henry.
It's okay. It's just that it's sometimes things get missed on the on these frameworks, and I just wanted to sort of just give you the heads up, if that's okay.
Yep. No problem at all.
Brilliant. Thanks very much. It really went well. And I think the attendees looked like it was, the attendees for some reason are lower than previous years.
Yeah.
And it's probably due to the previous years there was more CPD after the trail of lockdown, where there was not much CPD. I think that's the reason. But it's about, there was certainly close to 50 online,
Yeah.
which was all fine.
No, it's good.
So it was good.
It's still worth doing, and people took value from it, which is, I think, the key thing. So
Yeah, no, it was well received, and obviously there's people are actually saying thank you very much for the presentation. It was all very interesting, etc. So it was all very good. So well done.
no problem.
I'll keep in
So
touch.
yeah, hopefully the recording. We had a couple of issues with the last recording on when it was the AUE one. So hopefully this one recorded okay. And will Ella be putting it on the CIBSE YouTube? I'm guessing, is it something like that?
Not really too sure, but I will speak to Ella about that,
Yeah,
and we'll sort out the links and get that
no
sorted
problem.
out. And this little bit won't be on YouTube. I'll
No, 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 no.
ask her
And
to edit this conversation out. Is that okay?
yeah, and do you want me to send you? I think somebody asked for a copy of the slides. So do you want me to send a
If
copy of
you
the slides through?
if you send me a copy of the slides to myself and Ella, and we'll
Yeah,
definitely get those posted as we go, and I'll make sure that we actually get you the recordings
no problem.
back to you. But it was really good. It was very comprehensive, and it covered all the bases. And around 2000, I remember putting one of the first Coney monospaces in at Liverpool University, and it was quite a journey because
Mm,
the guys installing it had not done it before.
no, no.
So, but 1999, I think it was, in Mulberry House, was the first one and we had a few hiccups with it as well.
Yeah, I think I was there at that point in time, and yeah, it was funny times really, because we were figuring out a lot of things.
Yeah, it was a funny times, yeah, but it wasn't. Okay, I'll leave you to it. Enjoy the
Thanks,
rest of the
Henry. Have
day,
a good day. Take
Graham.
care. Bye
As
bye.
ever, thank you. Bye bye now.